So thank you all for joining us today. This is the 5th season for the IGCP648 virtual seminar series. For those who don't know, so I'm Luc Doucet, I'm your host. So I'm really happy to start this new season with you guys. It's really a great pleasure. And for this first talk, for this 5th season, so we are starting with Dr. Nicolas Flament, a senior lecturer at the University of Wollongong in Australia, presenting Setting the Lower Mantle Free. So Nico investigates deformation of the solid Earth over the tens of millions of years, merging geodynamics models with global geological observation in collaboration with earth scientists in academia and in industry. Nico, the audience is all yours.
Thank you very much, Luc. Thank you for the invitation. Thank you for the introduction. It's a privilege to be here tonight. It's a bit late in Wollongong, but it's very special to be talking to this group. This project has its roots actually in a small workshop from the IGCP in Townsville in 2017, if my memory is not too rusty. Unless it was 2017, I think. When Nicole Janusek was then at De Beers, and I started a collaboration. This became a linkage project, so partly funded by De Beers and partly by the ARC. The research team here consists of 4 early to mid-career researchers. Omar Boudou is a postdoctoral researcher at Wollongong. Simon Williams will be starting a future fellowship at UTAS very soon in Tasmania. And Andrew Meredith is a Marie Curie Fellow at Leeds. The title here is a bit different to the title of the paper. It's a bit less boring. So it's about setting the lower mantle free. I won't be talking about LLSVPs because it's a tongue twister, and also they are a seismic object. And then the models I'll be presenting, I don't have seismic model objects. I'll be talking about blobs. It's a lot easier to talk about blobs. So these blobs that I refer to, they're deep in the earth, and we've known about them for about 35 to 40 years, or scientists have known about them for 35 to 40 years. And here's one view of the blobs from model S40RTS. There's a blob under Africa and there's a blob under the Pacific Ocean. And these blobs extend to some height, and it depends how they're mapped, and they have an area that covers about the same area as the continents at the surface. We'll be looking at blobs a lot, so I'd like to introduce a second view of blobs, and this one is a view, it's in 2D, so a map cross-section. It's about 200 kilometers above the core mantle boundary. It's the same model as 40RTS, and that's the model I'll be using throughout this talk. And you can see again, we have the blob under Africa and the blob under the Pacific Ocean. And these can be mapped or have been mapped by scientists in different ways over time. There was an important insight that came from that mapping. And that's work that was started by the late Kevin Burke, and then Trond Torsvik and others joined the team. The insight there that was important is that when looking at these blobs, and mapping them using a -1% contour. I believe that was for model S mean, which was a mean of several, I think 4 S-wave models, demographic models. Taking the -1% contour, so velocities, and that's what I didn't say about the blobs, and maybe I should have. The blobs have velocities, shear wave velocities that are lower than ambient mantle, which indicates that they are hotter than ambient mantle. There's debate about whether they might be compositionally distinct as well, but the key message here is that they are hotter. That's what's around them. Now, this mapping using the -1% contour showed that the blobs would look like this, and then reconstructing large igneous provinces to their time of eruption and plotting them on top of these blobs really showed a correlation. That was that, especially in the African hemisphere, where there's more of these large igneous provinces, there seems to be a correlation between the blobs and the large igneous provinces. So a large igneous province is the kind of volcanic eruption that can wipe out the dinosaurs. Okay, so one of them down here would be the Deccan Traps. And that's about 65 million years ago, and it's been linked to some extent to the extinction of the dinosaurs. There's fewer of them in the Pacific realm. They also don't extend much beyond 300 million years ago. And because it's difficult to do analysis with few samples, the other insight was to use kimberlites. And these kimberlites also tend to cluster around the African blob. There's no kimberlites on the Pacific blob because kimberlites are on continents, and there's been very few continents above the Pacific blob in the last 500 million years. And then this became an exciting idea for tectonics. One problem with tectonics is that going back in time, there's no ocean floor to reconstruct. So the oldest ocean floor is probably about 200 million years old. And so one is left with paleomagnetic data as the primary tool, and then geological observations that are more traditional, such as whether an arc, whether a subduction zone might be present. Paleomagnetic data are good to constrain paleolatitude, but not paleolongitude. And so the relationship I presented on the previous slide was used to suggest that perhaps the blobs had never moved or had moved very little over time, which would make it possible to reconstruct any plate carrying a large igneous province or kimberlites. So its latitude could be known potentially from paleomagnetic data, and then its longitude could be inferred by pinning it to the edge of a blob, the closest blob. Two examples here, from one from Siberia, 355 million years ago, and another one from Africa at 500 million years ago. This African one here is important because it's at the African plate in tectonic reconstructions is at the top of the tree. I mean, it's important, but they're both quite important in terms of the concept of going to reconstructing longitude. There are two major assumptions here. Is that the blobs have been rigid and fixed over time. And this is the assumptions I'm going to challenge today. Not the only one having challenged them, and this is work from Alan McNamara, that he reused to present the work, or to introduce the work I'm presenting today. The understanding from the kind of model I'll be presenting today is that tectonic plates or oceanic lithosphere sinks into the Earth's mantle, and as it sinks deep, it pushes away from it material that's hotter. And that's the main way in which these hot basal mantle structures are created. And at the top here, what's shown as well is again the blobs, and now a different set of hotspots that are plotted on it to show that this relationship holds mostly, except for perhaps along the Americas here. So the idea here would be very much that the blobs in the very deep Earth are linked to subducting slabs. Now, models or tectonic reconstructions suggest that slabs have moved over time. Not so much in the last 200 million years or so, which is what I'm showing at the top here. And so models that use tectonic reconstructions going back to 200 million years ago would show that the blobs actually are where they are, and there's hardly ever a subduction zone on top of them. However, when one starts going further back in time, a thing to flag is that things become more uncertain, both for relative and absolute plate motions. However, it seems unlikely that subduction zones did not cross over blobs. Okay, so if one accepts that from subduction zones, slabs are going to sink into the deep Earth, the picture at the bottom here directly suggests that some slabs have crossed over the African blob and the Pacific blob in the last 400 million years. So if the cartoon depicted on the previous picture is true, it seems unlikely that the blobs have been fixed through time. And that is this cartoon here, where simply tectonic plates coming down push the blobs. So to test this idea a bit further, I carried out a series of models that are mantle convection models driven from the top. What they use as input are global reconstructions. They're the first set of reconstructions that went back to 1 billion years ago. And they have continuously closing plate polygons, which is important to obtain velocities at the surface and plate boundaries. This is then assimilated into a modified version of SITCOM-S, essentially assimilated or forced into a modified version of SITCOM-S. We impose mainly two things. We impose the velocities at the surface, and then we impose the temperature in the shallow earth for the lithosphere and the subducting slabs. I run these models with about 13 million points, and they take around about 150,000 CPU hours per model for 1 billion years, which is not very cheap, but it's not very expensive either. So I could carry about, I think in that paper, I presented about 20 models or so. And in the bottom here, I would like to take an opportunity to familiarize you with what we're going to be looking at. On the left-hand side is what goes in, the age of the ocean floor and the velocities and the location of the continents. So you can see India here. And on the right-hand side is what comes out of the model. In this case, we're looking at subduction zone or subducting slabs, and it's an iso surface of temperature, and it's colored by depth. So the slab is lighter where it's closer to the surface, and it gets darker, deeper into the mantle. So we'll be looking at things like that. The initial condition is unknown. It's 1 billion years ago. It's deduced from the tectonic reconstruction. What we do from the tectonic reconstruction, we insert slabs with a 45-degree angle to about 450 kilometers depth, and then straight down, and then they thicken a bit in the lower mantle that is more viscous. In this case, I've assumed a viscosity jump of a factor of 10. And then at the base of the mantle is the other important thing, is that we have a layer, which is the thermal boundary layer, but also in there, in some cases, I nest a compositionally distinct layer and I vary its density. Okay, and its thickness is just over 100 kilometers, and it represents 2% of the Earth, of the volume of the mantle. On the right-hand side is a view of this initial condition in 3D, and you can see the slabs down to 1,000 kilometers, I believe, in this case. And then you can see the continents at the surface. I'll just give you one more key here, which is important, is that these continents have also used a chemically distinct material for them, and this will come back towards the end of the talk. So essentially, we will be tracking the crust for the continents and a basal layer for the composition. Everything else is temperature. And as you can see on the left-hand side, sorry, I'm giving a bit more detail perhaps than I should, but I saw there's some geodynamicists in the audience. We have a adiabatic gradient here, so adiabatic heating in the model. And here's the subduction history that I imposed. So this is work by Andrew Meredith. It's his original reconstruction modified to be in the no net rotation frame of reference. And again, this will be important a bit later. I'm just flagging this now. For now, all we can do is simply look again at the history of subduction in that model, going back in time. So the last 250 million years here, with the warmest colors are the present day, and then getting older and older. And you see that again for the last 250 million years, the subduction zones are largely away from the blobs. But as we go further back in time, this is less and less and less true. So you can anticipate what the result will be. And let me show you some of that result. This is an animation, and I played it several times. This is smooth. It's in 1 million year increments. This is not the analysis I'll be carrying out. I'll be using 20 million year increments later on. At the surface, we have the coastlines or the continental blocks, tectonic blocks. You might be able to make out Africa here if you follow the west coast of Africa, if you follow my pointer. We also have plate boundaries. So this would be the Atlantic ridge that I just lost because the movie started again. So all these plate boundaries here. So this is the North Atlantic ridge now that starts earlier. And inside, we have two surfaces. We have the blobs that are hot, colored by depth, and the darker colors are shallower. And then we have the slabs that are cold, they're colored by depth, and the darker colors are deeper. Now, when we look at this, what do we see? We're looking at the African realm, the African hemisphere. And what you can see is that coming towards the present day, you see a blob that assembles that does resemble the African blob or seismically imaged LLSVP. And as we're going to jump back in time, train your eye, because what we'll see is that actually 200 million years ago, we have three smaller blobs separated by slabs that have sat there for a long time. And then they've been pushed by newer slabs. And then over time, the slab remnants warm up so that we end up with only one blob. So there's two things from here. You can see immediately that the African blob is not fixed and its edges are not rigid. Okay. Now, this is a beautiful picture, but we need, well, I wanted to do a bit more work to go back to the original hypothesis. To do that, I had to do a bit more of that mapping. So here's one way to look at the same model I just presented you for the present day. We're looking at the predicted present day temperature as a temperature anomaly. It's again about 200 kilometers above the core mantle boundary. We can see we have a large Pacific blob and a kidney-shaped African blob. I showed you earlier this picture here. And what I'd like to do next, so this is the seismic tomography models S40RTS, 200 kilometers above the core mantle boundary. What I'd like to do is compare them. There is a proper way to compare them, which I'm currently working on with colleagues, which is to seismically filter, to convert this model to seismic velocities, essentially, via mineral physics and densities, pressures and temperatures. And there's a second way to do it, which is the way I've done it here, which is cluster analysis. And that's inspired by work by Lekic and others in 2012. They worked with tomographic models. And they essentially said, okay, if a set of points at the surface of the model is classified into a number of clusters, 2 clusters, for example, so that the clusters distinguish 2 families of seismic velocities, okay? And that the way this is done, each cluster minimizes the distance to the mean, okay? And when you do this exercise, it's called k-means clustering. When you do this exercise for S40RTS, what you get is a fast cluster and a slow cluster. And the slow cluster is the blob, or the slow clusters are the blobs, okay? And the white cluster here is the fast one, and it's the let's call it the non-blob. And that's a 2.5D representation because it's an average for between 1,000 kilometers and 2,800 kilometers depth. One thing to note is that the area of the gray here is 34% of the total area at that depth, which is roughly, if you think continents at the surface, they're about 40%, but the part that's emerged is actually about 27%. So that's an interesting thing. Now, if we look at the model, at the flow model, I can do the same exercise, except that now instead of mapping, clustering seismic velocities, I'm clustering temperature anomalies, and I get a cold cluster and a hot cluster. So the hot cluster is the blob here. And again, here in this case, I get the same, it's a bit of a fluke, I get the same area, about 34%. And now that I have 2 maps that are in 2.5D, Rick, are you able to hear?
Yeah, I heard as well. I'm not sure what's going on. Okay, I got it. Sorry,
you.
someone need to be muted. Sorry for that.
All good.
Okay.
Let me see. Do I have control still? Yeah, I do.
Cool.
All good.
Sorry.
Thank you. No, it's all good. Things happen. So now I have my two maps and I can stack them on top of one another. And when I do this, I can highlight areas where the model is a blob and the tomography is a blob, which is in orange. So that's good. The other area that works is non-blob, and that's gray. So I call them true positive and true negative. And then there's the total area. And if I do this, and I can define a metric that I've called an accuracy. And in this case, the accuracy is 72%. I must highlight that the score is large because of the large area of gray. Okay. One could use another score that's called the sensitivity, which only takes the areas of blue, orange, and green into account, and the scores would be smaller, but the trends would be similar between models. And just to be complete here, the green area is a false positive, so the model thinks there's a blob, or the model predicts a blob, but the tomography, the flow model predicts a blob, but it's not in the tomography. And then there's the false negative, where there should be a blob from tomography, but there isn't in the flow model. So 72% is not too bad. If I were to use the sensitivity, it's closer to 50% what I would get. So now this was a constraint that was for the present day. And so that's not good enough for what I want to do. So I needed to have a constraint that goes back in time. And this is, again, it's inspired by the work of Kevin Burke and Trond Torsvik and collaborators. So what I'm showing here are large igneous provinces from Johansson and others in 2018, and kimberlites from Tapu et al. So I was not really inspired when I put that map together. There's diamonds and kimberlites, but what I did, I used diamonds for the large igneous provinces, okay, and the kimberlites are the disks. One thing I need to tell you about the Johansson database, it has the plume heads, so the lips, but it also has the plume tails. So it means that think Hawaii Emperor, for example, that seamount chain is in it, okay? And the same for Louisville, all the hotspot chains are in it. So that's why there's a fairly large number, 168 for the last 320 million years. As for kimberlites, in that database, there's 763. And here I'm showing them at present day reconstructed at that time of eruption in the no net rotation reference frame. Just to look at that in time, a histogram of what data do we have? Well, lips, we have a few up to about perhaps 30 in that database because we have the tails, okay? And here what I've done, I've rebinned everything into 20 million year increments. So it's on a sliding window of 10 million years, and that's to match my model output. And that's the only reason I'm doing that. And then kimberlites, there's more, and there's a peak that's well known around about 100 million years ago. And what I've done in the following, I'll be actually combining the data, and so we'll be looking at these gray. So instead of splitting here, I've lumped the data together. And now we're going to be looking at them. So this animation here will have two things. On the left-hand side will be with a mantle flow model, so things will move. On the right-hand side will be with a tomographic model, and things will not move. Diamonds will be large igneous provinces, and the dots will be the kimberlites. For the next slide, what's important to keep in mind, and maybe it's a bit too early to tell you that, but that distances are positive inside the blobs and distances are negative outside the blobs. So why do I talk about distances? What I'll be doing for each of these volcanic eruptions, I use pi-g plates to measure the distance to the closest blob, and I recorded it. So I'd like to show you what this looks like through time. And essentially, you can choose to perhaps look first at the left-hand side and then at the right-hand side. I'm going to play it a couple of times and try and convince yourself, well, in which case do I see that these diamonds or these symbols are closest to the gray background? I would say if you look at this, we're going back in time and it's looping, now it's going again. it's hard to tell, right? The jury is out. It looks like it's close to the tomographic image on the right-hand side, no problem, but it's also close to the moving blobs on the left-hand side, which is why well, to work this out, actually, one needs to get the numbers. And that's what we can look at next. And these are called CDF or EDF, empirical distribution function. They show the cumulative probability that a sample is at a given distance from sorry, I'm getting tired here. A given distance from the edge, in this case, of the blob is what I've determined, and that's inspired by work by Pavel Dubrovina and others in 2016. So what this shows, essentially, you can think of this as a histogram, but it's been unfolded, okay, and it's the cumulative distribution now. One important metric that I look at, or one easy one to look at or to unpack for you, is that 0.5 is 50% chance, so that's the median. So reading this graph here, you could come down here, and the median here is -1, and I've written my median like this here. So that means that in a median sense, the kimberlites and large igneous provinces that I've considered here are slightly outside of the blobs. They're within 1 degree in a median sense. Okay. For the tomographic model, they're slightly further out. So 50% is here, and that gave -4%, 4 degrees, sorry. And it was 1 degree. So that was good, but then I wanted to check if statistically that stacked up, which was kind of where there'd been a bit of a debate in the community about the stats of blobs and large igneous provinces. And so to the previous graph, or to the previous plot, what I've added now are random points. The way I've done this, the points are distributed in the same way in time. That's what I've imposed. Okay, so there's 931 because that's the sum of the two. I'm going to show you one iteration, but for each case, I've actually realized 1,000 iteration. So the temporal distribution of the random points is the same as that of the sample. And when I do this, chickenpox. Wow. So why do we have that? It's because kimberlites tend to cluster. Okay, so we'll look at that again. And we're going back in time, and you can see there's fewer and fewer. But what wasn't immediately obvious in the original plot I showed you is that the disks or the dots, the kimberlites, there's many of them. And that's why when I go random, I've allowed the points to be anywhere on the Earth's surface. There's times around 100 million years ago, in particular, when there's many kimberlites where there's a lot of red points on the map. Maybe I'll let it play once more. And so what I've done is the same thing for each of these points. I've measured the distance to the closest blob. And each time I did that, it gave me a thin gray line here, and I did it 1,000 times. I could have done it 1,000,000 times, but 1,000 was probably enough. And then I considered a statistical test that had 2 parts to it. First, I check that in a mean sense, that the mean of the blue distribution, and actually it was the absolute value because it's folded about. So I took the absolute values of the blue distribution, and I checked that the mean of the absolute values was less than for each single gray distribution, that the mean of the absolute values was less in the blue than in the gray. And the second thing I carried out is called the Kolmogorov-Smirnov test, and essentially it rules out the hypothesis that the true distribution could be drawn from the same sample. Essentially, it says that at a given confidence level, which I define as 95. So if that test is returned positive, essentially it means that the true distributions are most likely not identical. Okay, not drawn from the same sample. And so what I reported here is a fraction, and that fraction is for the 1,000 samples. if the fraction is 1, it means all 1,000 samples, all 1,000 random tests. For all 1,000 random tests, the blue curve passed the test. Okay, so that's what I have here at the bottom. And in the tomographic model case, you can see that actually there's a bit of overlap between the blue and the green and the gray curves. And so in that case, 30 out of 1,000 failed. So now I had a metric, and then I could play games where I could do this for many different models. So I showed you one tomographic model, which is T3 here, but I considered 7, and they're listed here. And then I showed you one flow model, which is C7 here, but then I considered 9 on this plot alone. And then I had 4 metrics. And I think I've introduced them all to you, but let's unpack this. The first one here on the left is the fraction covered by the blobs. In area, there was 34% here, 34% there. And the gray range here shows you the target, which is the tomographic models. The second one here is the accuracy with which, so it was the match when I stacked the blobs at present day. And I had 72%, I believe, here for C7 or something like that. So it's here. And then I did that, and I would do this between different tomographic models. That gives me my target. And so the target, and you can see that most flow models are outside. And then 2 more things, which was the median distance in the blue curves in the EDFs that I showed you. And again, the range, the target range is the tomographic models. And then finally, the result of the tests, of the statistical tests, which turns out to be close to binary on this plot. It's either everything passes or close to everything, or everything fails on this one here. Don't know how I'm going for time, Luke. I'm going a bit slow. Bear with me, I'll get there. Put it on the time of day. Okay, so essentially, I then varied a couple of parameters. I varied the viscosity of the blob in the model, and I found a sweet spot for a blob 10 times more viscous than ambient mantle. And the second one, which was important, is because the density of the blobs is debated. So I had that basal layer, and I varied its density with respect to the ambient mantle. And it turned out there's a sweet spot around +1%, but when one does that, the area is off. And so I went with -3% as the +1.3%, sorry, as the preferred in the end. I did many tests in the paper, and you can go check them out if you'd like, and I'd be happy to discuss them. There's one I'd like to highlight here today. Is the tectonic reconstruction. I showed it to you earlier in the no net rotation frame of reference. Actually, I had it wrong. The first plot I showed you was in the, I think was the straight paleomag reconstruction. Then when we go to no net rotation of reference, this is what the effect is. Essentially, the volcanic products are pushed to the southwest. Okay, you can see from here, this cluster is pushed to the southwest. And so that results in a push out away from the blobs. Okay, so to illustrate that, tomographic models at the top here and in the middle row, you can see that the distances with the original tectonic reconstruction, generally the volcanic products are within. So these are positive median distances. That means that in a median sense, more, if you want more volcanic products are within the blobs. And then when we go to no net rotation, they tend to be pushed out. So we have negative median distances there. Statistically, the difference are not very much. What we found for the flow models, and that's why I want to highlight here today, it's relevant for the flow models to go into a no net rotation reference frame, and that's been known for some time, to match the present day structure of the mantle. Essentially, this is the main difference. You could argue that this and that doesn't change, and the areal, the fraction of the mantle, it doesn't change much. Let me unpack this for you. This is the plot you saw earlier. So in here, I used no net rotation reconstruction as the driver of the flow. And if I go to and the score is 72%. And if I go to a reconstruction with net rotation, this is what I get. So at present day, everything is screwed up and the accuracy is down to 58%, which is a big drop. Why is that? Because it's known essentially, this is a bit different. The Maxwell Rudolph and Shizhong study was looking very much at what was in the mantle. We removed the net rotation from the top. So it's a bit different, but the effects when I look at them are quite similar. Essentially is that with net rotation, there's a shift of structures in the deep mantle, which is why we remove the net rotation from the surface. There is still some net rotation in our models because these come from lateral viscosity variations. I want to do two more things and each of them will be short, I promise. I'll try to keep them as short as I can. There's a cool thing about the blobs. So there's a very cool paper from 2007, and a fair bit has been written about this paper since then. The idea on the left-hand side is that if one has an Earth with no continents, perhaps the steady state of convection would be one super blob and one major downwelling. Okay, downwelling, so that's a 1 degree 1 Earth, essentially, if one thinks in terms of spherical harmonics, and one super blob. But if one imposes a supercontinent at the top and a girdle of subduction around it, there might still be a super blob, but there would also be a blob under the supercontinent, and that's a degree 2 Earth now. Now, in models similar to the ones that I just presented to you, they're by others, and they didn't extend as far back in time. The main two difference, and the main difference really is they didn't extend as far back in time. What was found is that the African blob seemed to be largely there by 200 million years ago. And what we found, which is very interesting, is that when we push that back in time, it doesn't really work that way. Because in the particular scenario we considered, and it's a scenario, then it's got all its uncertainties, around the West Gondwana block here, there's a lot of subduction around 740 million years ago. That's going to go down into the African hemisphere. It stayed there for some time. And these slabs will be then, you will see slabs in the deep earth, and then there's two more slabs, Paleo-Tethys northern margin here, and the Gondwana western margin here, that are important in that they will just push blobs together and make the remnant slab disappear. Let me show you this in 3D. So these are gorgeous figures made by Omar Bodur. What he's showing here is the kind of plots you've seen already a few times now with 500 million years ago, and he's added there with tracked subduction zones going down. And this is the subduction zone going from 740 million years ago down to 500 million years ago, where it is at that time. And so that's the Western Gondwana slab, we've called it in the mantle. And it's still here at 80 million years because it's such a large body and it's a diffusive time scale. So it cools down, or it warms up, sorry, and it decreases in volume very slowly over time. Possibly, it possibly takes up to close to 450 to 500 million years for that slab to warm up. And then it's pushed from the north, Paleo-Tethys, and from the south, from the West Gondwana margin, which is what assembled in the movie I showed you earlier, the African ASVP. I'm going to show you what this looks like in 20 million year increments, just so you have the full picture in time. We have blobs early on, and at 740, I missed it, but we had this material coming down. We can track the WGS, Western Gondwana slab. I think it might be that one. And you see it's between blobs, and then it will be eventually warmed up. Maybe I missed it. It might have been another one. And we'll do it once more. And now I want to focus on the reds. And what you can see, the reds, these blobs in the African hemisphere, there's a fair bit of motion. And again, it really comes together back in the last 200 million years for sure. And in most of these models, actually, it was in the last 100 million years. So it jumps around a lot in 200 million years, in 20 million year increments. So just for something a bit neater, I'll just come back to this one again, and I think the West Gondwana slab is this one, and it just warms up slowly, and it will eventually become part of the blob. Okay, so that tells us actually that potentially some slab material is part of these blobs, which is for chemistry, geochemically, it's an interesting thing to consider. And Luc, your paper a few years back was an inspiration for what comes now. So I'm sticking my neck out a bit here, and please feel free to slam me if you must. But essentially, and I'm not talking to you in particular, but to anyone in the audience, very deep mantle anomalies have been interpreted in terms of hemispheres for a long time. So here we're looking at 208 to 204 lead isotopes in hotspots. And it seems that essentially there was a band which was called this southern hemisphere, which is a bit weird, but this band here where the anomaly was positive, but everywhere else it seemed to be negative. Okay, and again here shown that this is the original paper, I believe, from Hart in 1984, and it's shown in a 207, 204 against 208, 204 lead isotope plots. And this was recently revisited. Instead of having North and South hemisphere, now the hemisphere become Africa and Pacific hemispheres, which is nice. It's the blobs essentially. The results I must highlight depend on which plumes or hotspots are considered. Okay, and here you can see there's a number that are shown, and then there's a number that are highlighted, which are the ones that are used in more detail for the analysis, is my understanding. But essentially here we're now looking at 208, 204 lead versus 206, 204, and for two different hemispheres. And my basic understanding here is that there's the northern hemisphere reference line here, onto which these lips or these volcanic products that are above the deep Pacific blob fall more or less quite nicely. However, in the African realm, there's something that's a bit amiss. And it was proposed that what's amiss or what's different might be input from upper continental crust. And so we had the opportunity with the models I showed you, and I mentioned earlier, we tracked, or we had chemically distinct continents. And this is a bit of an undesired effect in the models, but what happens essentially when there's a continent next to which there is subduction, the subduction will just erode some of the continent. And even though the continent is lighter, it might be entrained to depth. And so we mapped that because we could. And what we're looking at here is on the present day, on the left-hand side, you can see the areas that have more than 5% continental crust in the mantle colored by depth. And the same now on the Pacific side. And essentially it snowed more continental material in the African realm than in the Pacific realm. And it's not unexpected because there's been more continents above the African blob than above the Pacific blob in the last 300-400 million years. Before that, it's debated. Let me just show you a movie of that. African hemisphere on the left-hand side and Pacific on the right-hand side. And you can see a lot more coming down here on the left-hand side. And I think these might be the key area of the WGS. And then a lot less on the right-hand side is the key. I'll just do it once more. So this was that key area of subduction early on. And then you'll see a lot coming in from around here as well. With this, I didn't do too badly for time and just borrowed 5 extra minutes, a bit less time for questions. So to conclude, I hope I've convinced you that the history of volcanism is as compatible with moving blobs as it is with fixed blobs. So we used to have that idea that blobs must be fixed. Well, they may be fixed, but they may not. And if they're not, this is consistent with current understanding of global geodynamics, at least for these models driven from the top. So the new challenge is to find a model driven from the bottom that would that would anchor subduction essentially. And that's a challenge because it needs to be fully dynamic, which the models I presented to you aren't. What I showed you then in the models I looked at is that the blobs could come together and break apart, similarly to continents at the surface. So maybe we have super blobs and blobs. Or maybe it's just that tomography, as it progresses, will tell us that actually there's a lot more to the blobs. An interesting aspect, I think, is that the African blob may have come together in the last 100 million years, rather than having been fixed and assembled for maybe 550 million years or more, as previously proposed. And finally, the African deep mantle domain could be enriched by subduction of continental material. Thank you very much for your attention, and I will very happily entertain any questions.
Thank you very much, Nico. Very, very good. Yeah.